We are having today a talk about the marine geology because geological mapping and modeling and also the geology does not know any political boundaries. It also doesn't know the sea-land boundary. And I'm very happy that Aileen Bohan, I hope I pronounced this correctly, Aileen, from from the INFOMAR program at the Geological Survey of Ireland, is giving a talk today about an interesting topic, meaning combination of many methods in order to picture the seabed geology and the seabed geomorphology. Aileen is a marine geologist and she is also a hydrographer. She is contracted by the INFOMAR program at the GSI, at the Geological Survey of Ireland. And along with marine geology, she works at GSI on inshore survey fleet, on an inshore survey fleet of 5 vessels, interesting, and acquires and processes hydrographic and geophysical data. You will hear more about the geophysical data later. She is also working with GEPCO and with the Nippon Foundation of the GEPCO Seabed 2030 project. And she has mapped the seabed in the Arctic, Atlantic, Southern, Indian and Pacific Oceans. My name is Christina Asch from the Geological Survey of Germany, which is a Federal Institute for Geosciences and Natural Resources. I'm honored to be the chair of the Geological Mapping and Modeling Group together with Philippe Calcagnon from BRGM, Hans-Georg Krennmeier from Geosphere Austria, and Irini Sandaniri from the Greek Geological Survey, and I will be guiding you today to our meeting. And enough words from my side. Our main person today is Aileen. Aileen, please, the audience is yours.
Thank you so much, Christine.
You're welcome.
Hi, everybody, and thank you so much for joining me today. My name is Aileen Bohan, and I'm here today to talk about INFOMAR, the Irish Seabed Survey, and our newest product that we're developing. So a series of marine geoscience reports based upon observations in the data we collect. So today I'm just going to start with a little overview of INFOMAR, how we map the seabed, before a brief look at the geology of Ireland, before going into our marine geoscience reports, and a few of my favourite features. So I think Christina covered me pretty well, but to start with, my name is Aileen, and as Christina was saying, I am a contractor with INFOMAR at the Geological Survey, and I have been there on and off for nearly 12 years. I graduated from Trinity in geology, and then I did a master's in UCC in exploration field geology, and I was specialised in mineralised vein systems in West Cork. However, when I graduated, the world was in a global recession. There wasn't a lot of work available, but I got extremely lucky getting a job cleaning data with INFOMAR, where I've been ever since. In 2017, I then won a scholarship to attend the University in New Hampshire and complete the Nippon Foundation GEPCO postgrad certificate in ocean mapping, as well as a Cat A in hydrography, before returning to INFOMAR. As well as INFOMAR, I also do work for GEPCO and working on our project, the Nippon Foundation GEPCO Seabed 2030 project. And this ambitious project, we aim to have the global seabed mapped by 2030. So wish us luck. So with that, I'll just give a little overview about INFOMAR. So INFOMAR, it's the obvious acronym for the Integrated Mapping for the Sustainable Development of Ireland's Marine Resource. And it's jointly managed by the Geological Survey Ireland and the Marine Institute, and funded by the Department of Climate, Energy and the Environment. Here on the right, you can see one of our finest products, and this shows the real map of Ireland. And you can see in red here, it shows the extent of Ireland's EEZ and our extended continental shelf limits based on recommendations from UNCLOS. And you can see it's an extremely extensive area if you look at this area within the red line. Our sea area, it's nearly 10 times the size of the land, making us almost the size of Germany if we could include it. The early work on the seabed mapping, this was carried out in the 90s by the Irish Petroleum Affairs Division for our submission to UNCLOS for the extended continental shelf limits. And this really demonstrated the need for a systematic seabed survey, leading to the initiation of the Irish National Seabed Survey, which ran from 1999 until 2005. And this aimed to map the areas deeper than 200 metres. INFOMAR then picked up in 2006 with the aim of filling in all the areas less than 200 metres deep. Down here, you can see our fleet of vessels, our newest vessel, the Tom Crean, and the Celtic Explorer. These are our large boats, and they generally work 30 nautical miles out. And then we have the inshore fleet. So the Mallet, the Curie, the Geo, the Lear, and the Galtzy. And our inshore fleet, these work from 30 nautical miles right up to the coastline. And generally in the summer, you'll find me on the RV Mallet somewhere around the country, mapping away. So INFOMAR kicked off in 2006 with the aim of completing 26 priority bays and 3 priority areas, as you can see here on the left. The second phase kicked off in 2016 with the aim of mapping the remaining areas in the Celtic Sea to the south of Ireland and the Atlantic to the west, as well as lots of inshore areas. So it's 2025, nearly 2026. How are we doing? Well, following a fantastic 2025 survey season where we were blessed with lots of good weather, you can see what we have left here to do. So the green is obviously everything that was surveyed. The orange was surveyed, but the data is still in processing. And the areas in blue are what's left. What the map doesn't show very well is the tricky inshore areas that are left. So you can see here in the west coast, in these inshore, there's lots of islands. Up here to the north, it's very steep cliffs. So the areas that are left are going to take a while to do. They're difficult areas. So wish us luck for the 2026 survey season, please. So I'm talking a lot about mapping the seabed. So I'd like to just clarify, what do I mean by that? So generally I'm talking about depth and the shape of the seabed. And how we use to map this, we generally use acoustic methods, such as echo sounders. So this means we'll send out an acoustic pulse. The pulse will hit the seabed and bounce back. And measuring the time that it takes, we can calculate the depth. Traditionally, depths would have been measured by a lead line. Then in the early 20th century, saw the development of the single beam echo sounder, which measured depths directly beneath the boat. And then I believe the first commercial multibeam was in 1977. And you can see an example of a multibeam there in the little infographic, and that will measure a swath of data. And so like mowing the lawn, you can go up and down, and get 100% coverage and really get a 3D picture of what your seabed looks like. Why do we collect bathymetry data? For everything. For INFOMAR, primarily for navigation. We collect our bathymetry data, and this goes to the UKHO, our primary charting agent, to produce the nautical charts. But really, I mean, the bathymetry data, we need this baseline data. If we're going to protect our oceans, we really need to know what's down there. For any kind of modelling, for sea level rise, for marine spatial planning, everything, we need a good quality seabed map. So from our multibeam, the data sets that we get out of our multibeam, we get 3 georeference data. So primarily, we get bathymetry. So these are our depth information. And from this, we can then create lots of products such as contours, shaded relief, slope products, rugosity, point clouds, etc. But as well as measuring the time it takes for the signal to get to the seabed and back, we also measure the intensity of the signal, of the returning signal, and this, or the backscatter. And this gives an indication as to the relative hardness of the seabed. And coupled with sediment samples, we can use this for the creation of sediment classification maps. With some additional data, we can then make habitat maps and better understand the ecosystems of our seabed. So it's really important information to have. Finally, the third data set we get is water column data. As well as our sound pulse traveling through the water column and hitting the seabed, we can also measure where our sound pulse interacts with things in the water column, such as fish and their bladders, or gas seeps and bubbles. We can use this water column data to map shipwrecks to ensure structures such as masts, which might be hard to resolve and could be a hazard to navigation. With water column data, we can ensure every additional bit of data is collected. Though this does give extremely dense data, so it can be a bit hard to handle. And you can see a few examples there. So that shows you a fish shoal there on the left. And you can just see the big cloud within the water column. As well as our multibeam data, some of our vessels will also collect sub-bottom data, giving us information about beneath the seabed. And this reveals the sediment structure and the thickness. On our sub-bottom viewer on the INFOMAR website, you can see here, so all the areas in green have sub-bottom data available to download. As well as having the data to download, we've also developed an automated process to develop these sub-bottom plots. And this is so you can have a quick look at all of our different sub-bottom files, and if you want to try and find features. And each of these plots, they have the sub-bottom data that you see here in the top. Oh, sorry. Sub-bottom data that you see here in the top. Then we have our bathymetry data and our backscatter data. And you can see here we have our overviews, and then we have the survey specific information, such as the instrument that acquired the data. This particular sub-bottom data, this is from a mound in the Irish Sea. And I love this data. Like, look at the layering from the sub-bottom, it's just fantastic. You can see straight away the different units of sediments and the way that this is just outcropping out. Yeah, so that's our sub-bottom data. All of this data, everything is freely available on the infomar.ie website. And we have web viewers, you can download data, the shipwreck viewers, our reports, charts, everything's online. So do check out our website. We also have a range of blue scale maps, which were a product developed last year. And these are just beautifully presented bathymetry maps from around the coast of Ireland. So that was just a little overview of INFOMAR. So we'll go on to a quick overview of the geology of Ireland. And I have to admit, normally my talks are a lot more based upon the marine section. So this is the first time I've actually given a geology of Ireland presentation. So hopefully it goes okay. Because Ireland, for such a small island, we have quite a complex and long geological history, spanning nearly 2 billion years, beginning in the Precambrian, coming right up to the Quaternary glacial deposits. So I'm just going to play this video showing the paleogeography of Ireland and where we were throughout the different time periods. So starting in the Precambrian, Ireland was located somewhere down the South Pole. And these rocks can be mostly found up in the west, the northwest, and a small amount to the southeast. The oldest rocks of Ireland are found on a little island up here called Innistrahull. And I'm looking forward to doing the report for that because we just surveyed it this summer. And all of these rocks in the Precambrian, they've gone through several orogenies. They're all very metamorphosed. If we continue on into the Cambrian, we can see Ireland was separated and covered by a large Iapetus Ocean. And in this, so separated onto two different continents. The northwest of Ireland was on Laurentia, the southeast was on Gondwana, and covered by the ancient Iapetus Ocean, where a lot of marine sediment rocks formed in this time. And these rocks can be seen on the east coast of Ireland. During the Ordovician, and we saw the onset of the Grampian orogeny, or the Caledonian orogeny, also called the Grampian orogeny for this, and the initiation of the closure of the Iapetus Ocean. And this was obviously very significant for Ireland as it stitched together the northwest and southeast of the island along the Iapetus suture. I don't have that Iapetus suture on this geology map here, but it roughly runs southwest to northeast here. And it's along this belt that you'll find a lot of our mines, our mineralization has all occurred along this Iapetus suture belt. And it gave Ireland the southwest to northeast structural grain we see. When we look at this map, you can see bodies and rocks. And as we go through our reports, you'll see that there's a lot of, everything seems to be orientated southwest to northeast. And this is where this came from. So in this orogeny, when the southwest and southeast and northwest came together, a large mountain range formed to the north. So the Silurians saw high volumes of sedimentation in both terrestrial and marine environments and volcanism. Then after the final closure of the Iapetus Ocean, we saw the onset of the Devonian period. So what we're about 400 million years ago. And we primarily have two rocks types in Ireland from this type. We have our Caledonian granites in the west, northwest, and in Leinster here. And we also have the amalgamated Ireland was then on the southern margins of the continent of La Russia. And this was a semi-arid continent located at like mid-latitudes. So Ireland was hot, semi-arid, and dominated by rivers and alluvial fans. And these were depositing massive amounts of sediment as the Caledonian mountain chain to the north eroded away. And these rocks are mainly seen in the southwest, in Cork and Kerry. And this is the old red sandstone. So as time continues on, the Carboniferous saw Ireland at tropical latitudes, and the continent was flooded by warm tropical seas. We saw muds were deposited in marine and mudstones deposited in marine basins, while limestones formed on the shallow water shelf sea. And this, you can see, this is the light blue here. These carboniferous rocks cover much of the Midlands. As the Carboniferous progressed, we saw the seas deepen and then shallow again. And this results in a lot of our black shales, our turbidite sandstones, and our coal-bearing deposits in the west of Ireland, so around here. And then the end of the Carboniferous saw the Variscan orogeny. So this is compression from the south and resulted in a lot of east to west trending faults and folds, as well as the reactivation of those older Caledonian structures. The ridges and valleys you see in the southwest down here, you can see all these peninsulas separated by bays. These would have formed in the Variscan orogeny. And what we can't really see on this map is that the peninsulas are all made of Devonian rocks, while the bays in between them are made of underlain by Carboniferous rocks as a result of the Variscan orogeny. Following the Variscan, we don't have a lot of evidence of rocks on the geological record in Ireland. There is some deposits in the northeast, and there is still chalk deposits from the Cretaceous period, when we think that maybe most of Ireland might have been covered in chalk, but a lot of it eroded away. So the chalk deposits are only left in the northeast. The Tertiary then saw with or the Paleogene, apologies, sometimes the newer terms get me. So the onset of the Paleogene saw crustal stretching and an onset of volcanism. And this led to a lot of volcanism. So we have volcanoes on the east coast, and dikes and sills were intruded all around the country. And then finally, we got to the Quaternary and the onset of cold conditions about 2.6 million years ago. And this saw various glaciations as ice moved over and back across the Irish landscape and the continental shelf. And it was depositing and moving sediments into many of the geomorphological features that we see today. It really sculpted the bedrock and leaving lots of glacial deposits, which we'll be talking about shortly. The Ice Age ended about 10,000 years ago, but this left the layer of geological materials, and these are what we interact with on a daily basis for growing food, building material, and the material on which much of our infrastructure is founded. So that was just a little overview of the geology of Ireland. Hopefully it wasn't too quick. But I'm now going to go into our series of Marine Geoscience Reports. And this is what I really want to talk about today. So we wanted to do a bit more outreach and community engagement, particularly in the geological space, and produce more technical geological work, as well as showing some local appreciation, and as kind of a thematic extension of our Real Map and our Blue Map series, but with a bit greater text and a bit more information and research carried out. So generally, I'll identify features looking in the bathymetry data or the backscatter data, and then just try and gather any data that is available on these features. So obviously I'll have my multibeam data, but I'll also look for LiDAR data, seismic data, any kind of boreholes, vibrocores, drone data, and shoreline mapping. You can also use the nautical charts. These are great to get the current information, the ocean currents, that is, and then, or the met-ocean data. And then, of course, I'll use the historical data and reports. It's always great looking at the Geological Survey Ireland, and the reports from the 1800s are always so interesting to read. And then, of course, all of the academic and published research. Then there's a few additional data sets. So there's been the Irish Shelf Sea geomorphological map, and this was a automated procedure carried out by UCC to automatically detect a lot of the features. And sometimes I'll use that to try and support what my interpretations are, or to help me find additional features. So this just shows the features that have been completed so far. So we've covered a range of features from bedrock, structural, sedimentology, as well as more recent Quaternary events and glacial deposits, which are particularly evident on the seabed. To date, I've completed about 29 reports, and they're between 3 and 15 pages long. When we first set out, we hoped to make them between 2 and 3 pages long, but ultimately sometimes you get stuck in the rabbit hole, or the features are so interesting and there's a lot to talk about. So it can be hard to keep them short and to stay on track. So you can see that I'm currently working in the West Coast, and will continue working away all the way around the coast, identifying features as we come along. And the end delivery, hope, is a series of PDF reports, interactive story maps, all freely available on the website. This graphic just shows some of the reports that I'm planned to do, and they'll keep me busy for the next few months. So we'll start looking at some of the reports and the results. So we'll start in the west coast of Ireland. So you can see we are in the west coast in Galway Bay, and with the oldest rocks we'll be discussing today. So here's one of our bedrock geological maps from the Geological Survey. And you can see that this Galway Bay is very interesting. It lies on the meeting point between some of Ireland's oldest rocks, which you can see here, and our much younger rocks to the south. To the north and the west, so these rocks here, we have some Ordovician rocks, and these were originally volcanics and sedimentary rocks, and they would have been laid down on, so these were originally volcanic and sedimentary rocks, but they were later squeezed and altered into metamorphic rocks. These were then intruded by the Galway granite, which you see here in red, following the closure of the Iapetus Ocean. Much of the bay, and to the south and east, is Carboniferous age limestone. These would have been laid down in warm tropical seas about 340 million years ago. And these also form the Burren. This is one of our geoparks that is located here. Cutting through the bay, we've got the east-west trending Galway Bay Fault, and this marks the boundary between the older northern rocks with our younger limestones. And with our bathymetry data, it allowed for the refinement of this fault. So in green here, we've got where the fault was originally mapped out. But when we looked at the outcrops, we were actually able to refine the fault to being further north. Because looking here, you can see this rugged granite. It's kind of pinnacly and yeah, I'll stick with rugged. As opposed to here, we've got our flat-bedded limestones. This can be demonstrated a little bit better in our 3D map. So this is looking west along our granite limestone boundary. And you can see to the right, these are our heavily deformed boundaries. These are our heavily deformed granites. There's lots of east, southwest, northeast fault trends from the Caledonia orogeny. They're highly fractured. And then to the south of the faults, or to the left here, we've got our nearly horizontally bedded limestones with some fractures and faulting from Variscan tectonics. So you can really see the different terrain on either side. Again, this is just looking at Galway Bay. So this time looking east into the bay. So this time on our left, we've got the heavily fractured and faulted granites and metasediments. And to our right, we have our lovely limestone plateaus and our almost horizontally bedded limestones. You can really see I think you can really see the different terrains in this one. If we move a bit further west, we have the scarred rocks. These are deformed lower Ordovician rocks. So they're lower Ordovician schists and quartzites. So you can see there's kind of 5 islands here. Scarred Beag and Scarred Moor there together, and a bunch of rocks. Each of these rocks has an individual name, which I didn't include because the map was getting quite busy. And the scarred rocks, this is a rugged cluster of reefs and skerries, and they rise really steeply up from the Atlantic seabed. When we look at our bathymetry data, you can see that there's a range and a variety of structures present. You can see that there's this foliation here in the rocks from southwest to northeast. We can also see our principal set of faults. These are slightly curved from southwest to northeast. See these here and here. Then we have our later northwest, southeast orientating faults in red. There. And then finally, we have the youngest set of faults, which are our southwest, northeast trending, and these are in light yellow as well. And this differing orientations indicates that there is some kind of rotation occurring during deformation, as we can see by the various orientations. Around the scarred rocks, we can also see where our boundary between the limestone and the granites or metasediments is offset by a fault, a north to south orientated fault. So again, to the south, we can see our lovely bedded limestone. To the north, we've got our granites and metasediments. The red delineates the boundary between our granites and our limestone, whereas the blue is our north-south orientated fault. And it's always really nice being able to pick out these features in our exposed bedrock. So moving a bit further south into our Devonian rocks, our old red sandstone territory. So we're now at the southwest coast of Ireland. Off the coast, we have some of our most famous islands, and these are the Skelligs, and they're located here and here on this large rock platform just off the Ivory Peninsula here. The name Skelligs, it comes from the Irish word skellig, and you can see here, so that's Skellig Michael to the south, and Skellig Beag or Little Skellig to the northeast. We have here is an integrated 3D map of Skellig Michael, and we have the LiDAR data from and integrated with our INFOMAR Bathymetry data, giving a real 3D picture of what Skellig Michael looks like. And just to note that Skellig Michael, the reason it's so famous, it's got these beehive huts that you see here. So this picture is taken from Skellig Michael looking out at Skellig Beag, or Little Skellig. And these beehive huts, these were built by Christian monks between the 6th and 8th century, making the islands particularly famous. You can really see the ruggedness of these islands, see out here. So it's always very impressive to me that this was chosen for the Christian monks. One of the main features that is quite obvious from Skellig Michael here is this U-shaped valley in the center. This is known as Christ's Saddle, and it's where a fault obviously caused this. So at first I was finding the geology of Skellig Michael a little difficult to figure out. But then luckily, Pat Meir in UCC and Ken Higgs and Ronan Hennessy released a book last year on the geology of Skellig Michael, a field guide. I wasn't able to find a high resolution image of the book. So apologies for how the low resolution image, but that is the name of the book. And that is also where this geology map comes from. You can see this fault from kind of orientated southeast to northwest. So this is what causes Christ's Saddle, this feature, the U-shaped valley feature that you see there. So Skellig Michael, it's made of these old red sandstones. It was all deposited in a hot, semi-arid climate with flash floods eroding materials from the Caledonian Mountains to the north and transporting it into the basin via alluvial fans and fluvial systems. On Skellig Michael, the old red sandstone is dominated by fine-grained sand layers interbedded with siltstones, all characteristic of sheaf flood and fluvial facies, with some veins of white quartz also recorded on the island. If we look at the bathymetry, we can see that some of the Variscan tectonic structures and possible reactivated Caledonian structures. We've got two different orientations of faults. So one set is trending southwest to northeast in blue here. And then we've got our northwest, southeast trending faults. And what it seems like here, you can see that the northwest, southeast faults have offset our presumably older southwest, northeast faults. So these differing fracture patterns, which are clearly visible in the bathymetry data, suggest again a multi-phase deformation history. Here you can see some folded bedrock layers, folded bedrock contacts, apologies. It's always great fun trying to just draw out all the different faults and fracture patterns that can be seen. But I do look forward to automated methods to see what they come up with. So continuing with our islands, we're going to have a look at some younger rocks. So we're going to move to the Aran Islands, and these are on the west coast here, back to Galway Bay. And they're just at the entrance to Galway Bay. We've got our three islands, Inishmore, Inishman, and Inisheer, as well as some smaller islets around. And these are all made of Carboniferous limestone, again formed in the shallow tropical seas near the equator. Again, looking at our geology map, we can see that all Carboniferous. And in some places we can see where some paleokarst features. So in some places the limestone has dissolved or broken down in shallow depressions or pits, essentially small kind of sinkholes. And these would have formed when the limestone was exposed to the elements, not in the marine domain. You can see a few in the bathymetry here. And this is just south of the smaller islands. One to the south of the largest island on Inishmore, and perched on top of 100-meter tall cliffs, there's a Bronze Age fort called Dunengus. So you see this fort here, and it's about 3,000 years old. This is a model from Sketchpad that I found, showing the dimensions of these cliffs. So these are 100 meters tall, which is a pretty impressive place to build your fort 3,000 years ago. What's really interesting about here So firstly, you can see in the high resolution bathymetry, this is the seabed just beneath the cliffs of Dunangus. There is a lot of boulders and loose material. This area is completely exposed to the Atlantic, so it sees a lot of weather. It's a very dynamic area, and that's obviously reflected in the bathymetry where we have all this these boulders and loose material. And there's some really interesting research being done. And this is mostly being led by Rona Cox. She's a professor of geoscience at Williams College in Massachusetts. And basically they're measuring how the boulders are moving. So in 2000, I think most years they'll send teams to map out where the boulders were. So here we see, and this is all from Rona Cox's work, here we see a boulder in 2013, and you can see where, or a boulder field, you can see where all your various boulders are. 2013, Ireland was hit by some very strong storms from a lot of easterly winds. And what we see is in the, sorry, the mouse. Then in 2014, a lot of these boulders have moved fairly significantly. And some of these boulders are hundreds of ton in weight. And this is occurring 10 meters above the high tide line. So it's an amazing amount of wave energy, and the amount of movement was almost unbelievable if it hadn't been mapped so well. They found boulders of hundreds of ton moved almost 50 meters inland. So it's really interesting to see the conditions that this island is being hit with almost annually. So we're going to move on from the Carboniferous back into the Quaternary and some of our sediment deposits. So we're going down to the south coast of Ireland, and we're going to have a look at our submarine barracan dunes. And these I just love because they're fascinating. So after the Quaternary period and all the glaciation, there was a lot of sediment left over as the glaciers retreated. So thick layers of sediment in the Celtic Sea. And these materials have been reworked by tidal currents, and they form really distinct features. So we've got, sand waves, sand ribbons, and barracan dunes. And these are these crescent-shaped features that you see here. They cover a massive area of almost 7,000 kilometers square, and mostly seem to occur at depths between about 50 to 100 meters. They're quite low relief. So you can see from our sediment classification map here that the dunes themselves are made of sands while surrounded by coarser grain sediments. Yeah, so they're very low relief. So they're only 50 centimeters to 1.5 meters in height. So they can be easy to mix in the bathymetry, but they're very apparent in the backscatter, which I have in the back of this sediment classification thing. No, sorry, it's behind the bathymetry to really highlight the barracan dunes. We found them to be, they're approximately 1 kilometer in width from horn to horn. So from one end to the other. The dunes are very cool because they develop in areas where you've got some persistent net current direction. You've got a hard substrate, and you've got a somewhat limited but a continuous supply of sediment. And as you see here, so, excuse me, the dunes will develop with the horns that you see here on either side, pointing towards the current direction. So generally, the dunes that our dune fields indicate a net current direction from the southwest to the northeast. But this gets really interesting when you look at our residual current maps. So this is a residual current map that was modelled, done by Reeve et al. In 2022. And what you can see in the area, so this is our area of interest. It's extremely weak currents. And the overall residual movement seems to be to the southwest. However, if we look at our dunes, the horns seem to indicate that the net current direction was to the northeast. So we see a bit of maybe a mismatch between the residual circulation and our dune orientation. And we're not Some of the reasons that myself and my colleagues have suggested is maybe a morphological lag. So these could be fossil dunes and formed in different conditions that maybe had higher energy currents or in different directions. Another explanation could be some models within the current limitations. So this model could be based on sparse direct readings in both space and time, and especially in readings really close to the seabed. So we're in 100 meters of water, and these dunes go to a maximum of about 1.5 meters above the seabed. Maybe we're not capturing the near seabed currents as the water, whatever happens to the currents as they flow around the dunes. Additionally, the model could be based on lower res bathymetry, such as the EMODNet bathymetry grid, which is about 100 meters resolution, and probably wouldn't allow for for us to see the Barracan dunes. So that's quite interesting. And thirdly, we don't tend to. I tend to move towards the current model limitations, whereas my colleague, he tends to go for the fossil dunes. But one third thought is that maybe it was an evolving sand supply with the abundant sands after glaciation 10,000 years ago. As these sediments have been reworked and winnowed, we've reduced that supply. So we're hoping that we'll be able to resolve some of our questions, that at the next survey season, we'll be able to resurvey some of our dunes and try and see if there's any changes or migration. We didn't have a lot of time between the surveys when we surveyed in the past. I think there was a maximum of 2 years, and I couldn't see migration between the 2 years. But we're wondering, since 10 years has now passed, maybe we'll see some kind of migration. Sticking with our sediments, so if we go a bit further east from our Barracan dunes, we have this beautiful extensive sandwave field. And these are sandwaves, and you can see this here, I think from my cover image. I could look at sandwaves all day. I just think they're so beautiful, the patterns they make. And these range from 2 meters to 20 meters in height. And we've got wavelengths on the order of 100 to 600 meters. And you can see in the sediment classification map, I think they possibly made a slightly coarser material. Though again, that could be it just seemed to be some, yeah, no, okay. I'm going to stick with coarser material, maybe. If we compare some of our surveys, again, we see migration to the northeast, which is quite interesting. So this is in the top here, we've got a survey from 2009. And in the bottom, you can see this line here. So this survey is from 2016. And you can see that there has been some shifting to the northeast. Here, so I've coloured, obviously the red is where erosion is occurring and blue is where deposition. So you can see that there is a migration to the northeast. Again, if we look at this, this is obviously a very generalised residual bottom current map, but from 1970. But the net current direction is in the area is understood to be to the southwest. Then again, if we look at the shape of these sand waves, you can see they've got a steep stoss side, they've got their stoss side and this steep lee side, which indicates that the currents are moving to the southwest, but migrating to the northeast. So I don't know, is this to do with storm events or, again, some of what we were mentioning before with the Barracan dunes? Unsure. Again, further research is needed. Sorry, using a mouse is a bit difficult today. So that comes to the end of some of my favorite of my features. Maybe I can update you again in a year or so when we've completed more of the northwest and the southeast with a few more features. Thank you all so much for listening. If you want to have a look at any data or anything, please go to infomar.ie or contact us at info@infomar.ie. My email address is there, as well as my LinkedIn. If you have any questions Or if you have any of your favorite features that you'd like to suggest, feel free to throw them in. Thank you so much for listening.